All right, let's jump right into this explainer. Today, we're graduating from just writing basic database queries to building truly robust, high-performance applications. Seriously, if you've ever built an app that runs like an absolute dream on your local laptop but then completely falls apart the second real users touch it, yeah, you're in the right place. We're going to bridge that crucial gap between making something work and making something survive. Because think about it. Why does a query that takes exactly 2 milliseconds in development suddenly take 800 milliseconds in production? It's a massive frustration, right? The data's the same, the SQL syntax hasn't changed a bit, even the indexes are identical, but out of nowhere your app is just crawling. So what gives? Well, almost every production performance mystery traces back to a root cause hiding deep inside the database internals.
Writing a query? That's the easy part. Making it survive production is hard. We're about to embark on a bit of a journey here, moving from your very first basic connections all the way through the real trials of a production environment, so you can emerge with some genuine architectural mastery. Because let's face it, dealing with thread contention, connection timeouts, malicious users, and massive data loads, that's the real game. So, here is our roadmap for today's explainer. Number 1, connecting Python and MySQL. 2, going inside MySQL's 5 layers. 3, defeating SQL injections. 4, fixing the dreaded server gone away error. 5, optimizing bulk insert speed. And finally, 6, mastering your database stack.
Okay, part 1, connecting Python and MySQL.
At a fundamental level, to actually speak to MySQL, Python needs a driver, something like MySQL connector/Python. Python itself isn't a database, right? It needs a translator to talk to a specific vendor's system. And that is exactly why standards like the Python DB API or PEP 249 exist in the first place. They ensure that whether you're using the official connector or a totally different alternative, there's always a reliable standard interface for your code to use. And the standard workflow for this is pretty straightforward. First, you establish a connection using your credentials, host, user, password, the whole shebang. Then you execute your SQL commands using a cursor object. Now here's the catch. If you're modifying data in a transactional engine like InnoDB, you absolutely must explicitly commit your changes or they will just vanish into thin air. And most importantly, always close the connection to prevent resource leaks. Trust me, those leaks will slowly but surely kill your server.
Moving right along to part 2, inside MySQL's 5 layers.
Once we're connected, it's fascinating to see how a single SQL query actually travels down through these 5 distinct layers. It starts at your Python application layer, shoots across the network to the MySQL server layer, gets handed down to the storage engine, which is usually InnoDB, then interacts with the file system layer, and finally hits the physical hardware layer. When we talk about database tuning, we're really just trying to remove friction in one of these specific layers. Let's zoom in on layer 2 for a second. At the server layer, MySQL parses your SQL, and then the optimizer steps in. This thing is like a performance wizard. It calculates the most efficient execution plan based on your indexes and statistics. It's basically the brain of the whole operation. It looks at your query and literally asks itself, okay, should I scan this entire table or should I use an index? It calculates the absolute cheapest path before the executor actually runs it. Moving down to the 3rd layer, we hit the storage engine, where the buffer pool acts as a giant reservoir. It keeps your hot, frequently accessed data right in memory for pure speed, before eventually writing changes to the redo log for durability. The golden rule for production DBAs here? Size your InnoDB_buffer pool size to about 70% of your server's total RAM. If your data doesn't fit in that memory pool, you hit the physical disk, and boom, your 2 millisecond query is suddenly taking 800 milliseconds.
All right, part 3, defeating SQL injections.
Let's talk security. If you are directly interpolating user input into a raw string query, you are literally leaving the gates to your fortress wide open. You might think, oh, I'm just taking a simple username string from a web form, but if you don't validate or escape that input, you're actually handing a loaded weapon straight to your database executor. An intruder can exploit that tiny oversight and cause massive harm.
It's wild how an attacker can use a simple string to completely hijack your app's logic. They'll use a semicolon to just abruptly end your intended query. Then, they inject their own malicious command, like select true, to force a positive authorization and bypass a login check entirely. And finally, they'll toss in double dashes to comment out and completely neutralize any code you had written after that. It's elegant, sure, but it is absolutely devastating. So how do we fix it?
The difference between a vulnerable dev environment and secure production is simple. Always, always use parameterized queries. This is where the database adapter safely escapes the input for you, treating it strictly as data, not as executable code. Never format user strings directly into your SQL. Instead, use placeholders like %s and pass your variables as a separate tuple. The Python connector will handle all the safe escaping behind the scenes. It's a total game changer.
Moving on to part 4, fixing server gone away.
28,800. That is a massive number. It's the default wait timeout in seconds, which translates to exactly 8 hours. After 8 hours, MySQL will just silently close an idle connection. So picture this, your Python app connects, goes to sleep for the night, and then tries to query the database the next morning. But the server already hung up the phone. Boom, you get the dreaded MySQL server has gone away error.
When you inevitably see this error, you need a mental troubleshooting checklist. Are your queries taking too long? Are your data packets too large? Or did your connection just sit idle and expire? You might literally be sending an insert statement that exceeds the max allowed packet size. Or your network might just be randomly dropping long-running transactions. You've got to check them all. But you know what the ultimate systemic fix for this is? Connection pooling. Instead of manually establishing brand new connections every single time or letting single connections expire, the mysql.connector.pooling module gives you a reservoir of pre-established thread-safe connections, defaulting to 5. This massively reduces latency. Plus, pools can do a quick health check pre-ping before handing a connection to your app, which pretty much entirely eliminates that gone-away error while making your app lightning fast.
Okay, part 5, optimizing bulk insert speed.
Inserting data row by row might be fine for a single user, but in production, it is the slowest bottleneck imaginable. Multi-row batching, using execute many with batches of, say, 500 to 5,000 rows, is incredibly fast for standard API loads because it minimizes round trips to the server. But if you're dealing with massive dataset migrations, like millions of rows, bypass standard inserts entirely and use the load data in file command. We're talking a 10 to 20 times speed boost. It's ridiculous. And if you want to truly supercharge those speeds, wrap your inserts in explicit transactions so the database isn't frantically flushing to disk after every single row. If you know for a fact your data is clean, you can even temporarily disable foreign key and unique checks. Just please remember to turn those checks back on and reset your InnoDB flush settings afterward to ensure your data stays fully ACID compliant.
Finally, part 6, mastering your database stack.
All right, look how far we've come. You've evolved from just making a simple Python script talk to MySQL to actually understanding the deep architecture required to make it survive in the real world. A developer focuses on writing a query that returns the correct data, but an architect focuses on connection pooling, parameterized security, and InnoDB performance tuning.
So take these architectural lessons back to your own projects today. Take a hard look at your database connections. Your Python app might be connected, but is it truly protected, pooled, and performing? What's hiding in your codebase?